Effects Analysis Capabilities in GENESYS, presented by Brian Selvy. My name is Donna Long, and I will be your host during today's webinar. Brian is a Principal Systems Engineer at Vitek, where he is responsible for consulting and training functions. Brian has over 17 years of experience in the systems engineering of aerospace, optical observatory, and defense systems. He holds an MS in Systems Architecting and Engineering from the University of Southern California and a BS in Aerospace Engineering from Cal Poly. Before Brian gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Brian will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be made available within 1 business day. The recording will be published to Vitek's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to Brian. Welcome.
Thank you, Donna. Okay, so as Donna said, we'll go through and we'll give an overview with a bit of an example of the new FMEA capabilities coming out in GENESYS 2020. So here's a quick outline of the webinar that we'll be going through today. First, we'll start with just a very brief overview of what an FMEA is and why you would conduct one. We'll go through and we'll talk quickly about the existing capabilities that have been available within GENESYS for several years now. But then we'll transition into the new and enhanced capabilities that are rolling out now. We'll go through and we'll at least talk about mapping back to some of the fundamentals of conducting an FMEA in industry. And then we'll talk about really some of the things that are built into the schema extension for GENESYS 2020. The schema overview, then there's a number of additional capabilities that have been generated to help just from day one, being able to visualize and navigate that information within the software tool. I'll demonstrate those with an example, and then we'll wrap up and we'll try to save some time for questions at the end. Okay, so quick introduction to FMEA. So what is it? Why would you use it? So failure modes and effects analysis. It's a technique to identify potential failure modes in a system as well as their causes and effects. You can do it in multiple different ways. It's an inductive reasoning technique. It's very heavily tied to reliability engineering, safety engineering, quality engineering. But you can do it at multiple different points within your program or project within its life cycle. You can do it as a functional FMEA, which is a top-down approach that's typically done earlier on in your project life cycle. As you're capturing requirements, as you're defining your functions and doing some functional analysis, at that point you can do a functional FMEA. And then once you get into preliminary design, critical design, at the point where your physical architecture takes shape, you can do a physical FMEA, which is a much more bottoms-up approach where you're looking at the lowest level reasonable and then capturing causes and effects of your failure modes, and then also how they cascade up, the effects, how they cascade up to become transparent at the system level or at whatever level an external user would it be able to see that effect externally from the system boundary. Okay, so we'll talk a little bit more about the process in a couple charts, but in general, once those causes and effects are identified, then we can look at how we can mitigate those, right? So that we don't have critical failures. And that can be done in a number of ways. We could decrease the probability of occurrence or try to design it out so that the mode is no longer even possible. We can decrease the impact of the effect, or we could try to increase the probability of detection so that we know it has occurred as soon as possible and a responsive action can be taken. So a lot of times you'll hear FMEA, you may also hear the term FMEA with a C that's included. The C stands for criticality, and I'll try to touch on that in a few places throughout the presentation as well. They're very similar in what you do. Criticality introduces one additional concept of identifying a criticality level for certain industries. Okay, so when we went back and we looked at enhancing our FMEA implementation, we went back and we looked at a number of standards. And these are the ones that we looked at in particular to make sure that we were pulling out common themes, common ideas that are consistent with both US and international standards. So we looked at the IEC 60812. That's the ISO standard for failure modes and effects analysis. There's an existing MIL standard for US DoD military applications, MIL standard 1629. SAE J1739 used in the automotive industry. The next one down here, the AIAG, is also an automotive one. These are all very similar in terms of their process, their technique, and their reporting. There's a number of other domain-specific standards as well, many in healthcare, many others in aerospace, etc. But we tried to hit the ones that are, fairly high level, and we tried to create an implementation that is consistent with those. And of course, if there's any tailoring that you may need for your own particular industry, GENESYS would allow that tailoring within the schema editor as well. But this provides a consistent foundation from which you can create those customizations if needed. Okay, so just a quick look back on what the legacy capabilities were in GENESYS. So an extension was released in 2017 for FMEA. There's a legacy webinar on that as well. There's a user's guide. Lots of content if you wanted to go back and see where things stood up until now. But what it did was it introduced a schema extension that included a couple of additional classes here: failure mode, failure cause, and failure reduction. And so that allowed one to go through a journey of capturing failure modes that were generated or associated with some other element within one's model, and then look at ways that the failure could be caused, and then came up with ways to reduce the failure in one of those dimensions that we talked about, and then document the design journey back into the model to show how something in the model was updated, either through capturing it as a concern, a change request, or a risk, and then those would then get resolved and an update would be made in the model. There were also some additional capabilities in that schema extension package, hierarchy definitions so that one could visualize these on a couple different diagrams and views within GENESYS. And then the Excel connector for GENESYS had a number of table definitions to be able to pull the information out, and much more of a standard table that is more of the standard view that an FMEA engineer would be expecting to see the information. So that's where we were. Let's talk about where we're going and what the additional capabilities are in the enhancement that's available. So it's always good to go back and look at first principles to make sure that anything that we're going to do in terms of implementation, in terms of a process and a methodology and tool capabilities are tied back to those first principles. So what you see here, don't worry about reading all the words, but this is the general sequence of events that one would go through to conduct a failure modes and effects analysis. This is adapted from a textbook, Systems Engineering Analysis by Blanchard and Fabrici. The first three steps here, the first three functions one would accomplish are things that are consistent with what one would do in developing a system, doing your model-based systems engineering outside the context of explicit FMEA, defining your system requirements, doing your functional analysis, and accomplishing requirements allocation. That is talked about, those are capabilities that exist in the baseline GENESYS schema today and the Strata methodology. What we're going to focus on are the things that are over here to the right that are in this loop. And if we just look at those, the steps that we must go through and follow are identifying our failure modes, determining the causes of those failures, the effects of the failures, if there are any means of detection, if there are any current prevention controls, ways that would prevent the failure mode from occurring, And then we would go through and we would do, once we have identified the effects, the causes, the detection methods, preventions, we then go and do some scoring. We rate the failure mode severity, the failure mode frequency, the detection probability. We then analyze the criticality. We'll come up with a combined score called a risk priority number. And then based on that, we can decide whether to mitigate it or not. As one does this type of analysis, typically you'll come up with quite a long list of failure modes. And there's, you have to triage this. You can't address all of them at once. And so once those risk priority numbers are captured and calculated, you can then determine which subset of those you're going to go mitigate and try to address first. And then typically one does this multiple times throughout a project lifecycle. One will go through and iterate back through this process potentially for, at the preliminary design phase, the critical design phase, et cetera. And so you continually go back and update your analysis, and we'll talk about how that looks as well. Okay, so in terms of what the actual implementation looks like in terms of the additional new classes and types of relationships that are in GENESYS, we'll go into that in a little bit more detail, but just to give you a quick intro right now, there are these 5 new classes that are in the Schema extension. We have failure mode, failure cause, failure effect, failure detection, and failure prevention control. So these map back, as I hope you can see, back to the process flow chart on the previous page. And this, we've done that mapping to make sure that we have complete overlap and capability mapping back to the generic process. One new thing that has been introduced in GENESYS 2020 R2 is a new class called Mitigation Activity. And we also take advantage of that. So that's a new class that has been incorporated from the base schema into our overall FMEA approach. And the way that I'll show you that we can go through and create these examples, we can do the modeling either at sort of a general level or a specific level, and just keep that concept in the back of your mind. I'll show you what that means when we get into the actual example. But for anybody that's familiar with SysML, the systems modeling language, what I'm talking about here is sort of think, if you know what I'm talking about SysML wise, the general maps to the concept of elements of definition, and the specific maps to the concept of elements of usage. So it allows one to do abstract or specific modeling. And then when we do that scoring, the scoring is done on relationship attributes. And so we have occurrence, severity, and difficulty of detection. And I'll show you I'll show you both in the schema and then in the tool how you would set those. All right, so those are the key high-level concepts. Let's go talk about what they mean really in implementation now. So this is a bit of an eye chart. Don't worry about reading any of the specifics on here. The key point is that now with GENESYS 2020 R2, we're now getting to the point where there is an integrated uncertainty modeling schema. And so some of the capabilities that were introduced within R2 on the risk side, as I said, mitigation activity was split out from the risk class. This then allows one to address mitigations, multiple mitigations for a particular risk, a particular mitigation that could mitigate multiple risks, etc. It creates its own first class concept. So we have the concept of being able to do a really fully comprehensive risk analysis and monitoring within GENESYS now. There will be an extension of that will also be available for opportunity analysis, which is just think, the opposite of risks, so positive things that could potentially occur in the future to the benefit of a program. This is another extension that will be coming out soon. But over here on the right is all the FMEA stuff. And the point here is just that now that we've broken out this concept of mitigation activity, it is something that can be used for multiple different types of analyses. One on this, what I'm calling the specification space over here on the left, really tied into programmatic and requirement type risks. The other is in realization space. As we start to come up with our system architecture, both physical and functional, or behavioral. That's where we can start to get into the failure modes and effects analysis. That's really looking at what could go wrong with our system as it's getting designed. So two sides of the coin, integrated analyses, and GENESYS allows one to now do comprehensive uncertainty modeling within the context of your system of interest model as a whole. Okay, let's just now look at the FMEA schema. I redrew the elements on the previous chart in a slightly different way here. To me, it kind of looks like a lotus flower, so I'm calling this the lotus flower diagram. But let's kind of just walk through and look at all the different types of capabilities in here now. So we enter the FMEA analysis from either a component or a function, a port, maybe a link or an item that is introducing the failure mode. Recall I said functional FMEA typically starts with a function. Physical FMEA typically would start with a component, but there's also these interface classes that could also be the generation point. All right, so something's causing it. We capture the failure mode in the failure mode class. From there, we then can branch out and look at those three things that we talked about: failure causes, and a failure mode can have more than one cause. The effects, the failure effects, so what happens if the failure mode occurs. There are local effects, as I said, if you do a physical FMEA, those effects can cascade up within your hierarchy. And so you'll see that there's one additional relationship here called leads to or comes from. That allows one to say, hey, there's a local effect, there may be a next level effect, there may be a higher level effect, and this relationship allows to show the traceability up in effects to higher levels. And then we have the failure detection over here on the left, which is there anything within your system that would allow you to know if the failure mode even occurred? So it's that, is there a way to even understand from a transparency perspective if something happened, a bad thing happened? Okay, and then on the relationships, we have, for the failure cause, we have a created by relationship with the attribute of occurrence. That's where we're going to set the value for the occurrence. On the relationship between failure mode and failure detection, that's the detected by relationship, and it has the attribute difficulty of detection. And over here to failure effect, it's the effects relationship, and it has the attribute severity. The reason why we are setting the numerical values of these 1 to 10 scales on the relationship rather than the entity itself is that, recall, a failure mode, as I said, could have more than one effect. It could have more than one cause. Setting it on the relationship makes it context dependent. This failure mode in the context of a particular failure cause has a particular probability of occurrence. So that's why they're on the relationships. As we move on, as I said, there's this fourth concept of a prevention control. Are there ways within your system that you've designed it such that you're trying to prevent the mode from even occurring? If those are within your system, then we can capture those as failure prevention controls. Causes, detections, and effects can all be mitigated, and so we're tying it back into that mitigation activity class now. And then you'll see these items in blue. So everything we've talked about are really, the things in orange are analysis concepts, right? We're doing analysis within we're doing object-oriented, model-based FMEA now. If we want to tie that back into the actual, what we think of as the physical or functional elements within our model, we can use this embodied in relationship to essentially do an allocation. So if a failure effect is embodied in a particular function or component, we can make that explicit relationship such that when we go look at, for example, a particular component, we can see if it is affected by particular failure modes. We can see if it causes other failure modes. So this allows that traceability that really tie back into one's architectural model. Okay, so once we, on here, we talked about occurrence, difficulty of detection, and severity. Once we set those, we can calculate what I had mentioned before, the risk priority number. And there are slightly different ways. Certain industries have slightly different versions of this, but the one that is most common is each of these get rated on a 1 to 10 scale. So you'll see the baseline scales that are included within GENESYS here. And for each combination of failure mode, effect, and detection methods, you can calculate an RPN. Those numbers are going to range between 1 and 1,000, as you can see here. And as I said, part of that process is once you get all these, you can rank order them, and you can see which ones are most pertinent to address first. So that's how you actually use this to decide how to start deciding which ones you want to mitigate first. Okay, and then in terms of actual implementation within the tool, we've included a few capabilities that just allow you to, visualize, get to the information within the tool, all those sorts of things in a little bit easier way. So the first is we've added an additional facility. So those that are familiar with GENESYS, you'll know that there are different ways to essentially sort the classes within your Project Explorer. With this schema extension installed, you'll get a new one called Failure Modes and Effects Analysis, and you'll see just the classes that are applicable to conducting FMEAs. There are also a couple predefined hierarchy definitions. One will allow you to see essentially specialization and generalization. And so I'll show you this more in the sample model, but if you do the sort of the elements of definition, elements of usage concept, it'll allow you to see that visually, either on hierarchy diagrams or spider diagrams. And then also the other one is just a generic FMEA set of elements and their relationships so that you can see all the types of related elements either on a hierarchy diagram or a spider diagram. So those are already set up for you, and you can apply those to either of those diagram types, as I said. These can then be coupled with the new GENESYS 2020 R2 concept of rule sets, and they can also be combined with node templates that you can really further enrich the visual information displayed on your diagrams. So there's one new rule set that's also included, and you can use this as a template for further specialization for your needs or what have you. But this generic one that's included is the color code, all the various types of FMEA elements, and in just a standard format. If you like a different color format, you can obviously go in here to the rule set and change that if you wish. But this will allow you then to apply some coloring to those types of views. And then of course, the most standard way of viewing this information is in a tabular format. And so the GENESYS Excel connector, there is a table definition set that comes with it as well, an FMEA component view table that would be very easy to modify for a functional view table as well. But this then allows one to see all the standard information that is very consistent with the IEC, the SAE standards that I mentioned earlier. Okay, so talked a little bit about these capabilities in the abstract. Let's now look at it in terms of an actual example, and hopefully that'll help make all this stuff a little bit more concrete. So the system that we're going to look at, just as a very simple example, is we have a two-stage rocket. Okay, think any small booster, and it's a two-stage rocket to something to provide, payloads to low Earth orbit. Typically, each stage requires helium on board for pressurization and purging and some other functions. And so during ground fill, before the rocket is launched, all the helium from some sort of storage tank on the ground has to get pumped into these helium bottles on each of the stages. So the reason why I picked this is it's a very simple system, and it's pretty easy to understand the concepts going along here. So the idea is the concept of operations is, several hours before launch, the particular responsible engineer or technician will go out, open up this isolation valve, and then somebody in the control room at the right particular time will start to send automated commands to this valve called HV2 to open it up, and then will allow helium to flow up to the first and second stage fill valves. And then once each of the stages are starting to get conditioned for launch, typically in some order, typically first stage and then second, the first stage valve will open and the first stage helium bottle will fill. Once it reaches a certain pressure, HV3 would close, and then the process would be repeated for HV4. Okay, so pretty simple system, just a few valves, and it lends itself nice to an FMEA example. So for this analysis, we're going to look in particular at HV2, this remotely operated helium tank isolation valve, and HV3, this first stage helium fill valve. Okay. So let's go look in Genesis and see how we would actually model this. Okay, so I'm just going to switch over to Genesis, and I have a model set up already. You'll see over here on the left, I have my default facility set to essentials. So the first thing I'm going to do is go over here and flip it over to failure modes and effects analysis. And I will get all those classes that I mentioned that are now applicable to conducting these types of analyses. Okay, so the first thing I'm going to do is I'm going to go in and start thinking about my failure modes. Well, maybe one thing I can show you is I modeled a very high level physical view of my system first. And so I'm going to go open this as a BDD. And you'll see that at least for the context that we care about is our system context consists of ground support systems and our launch vehicle. And our launch vehicle has a first stage, a second stage, and a payload. And the portion of the scope that we care about for this, the first stage has a first stage helium bottle and a pressure transducer so that we know what the pressure is in the bottle. Same thing for the second stage. And then if I move over to the rest of the ground support, there's a lot of other ground support systems. Nitrogen, in this case, my rocket uses liquid oxygen and RP1 as the fuel. There's thrust vector control hydraulic component, water deluge for fire suppression during launch, etc. There's a lot of other ground support systems, but the one that we're focusing on here is gaseous helium, and I have all my main components that were on my schematic labeled over here or captured over here. Okay, so I have just the amount that I care about for conducting this analysis model. If I go over and start thinking about my failure modes, I can label them, I could model them generically if I want. So a valve, let's just think abstractly, a valve could fail open or closed. So there's a failure mode valve failed closed. There's a failure mode valve failed open. That could apply to any of those valves that I talked about, right? And so if I want to use the concept of specialization and generalization, I could model these abstractly first, and then I could model essentially a specialization of each of these for the particular valve. And so that's what I did here. The valve failed closed. I have HV2, that tank isolation valve failed closed, and then HV3, that first stage fill valve failed closed, okay? And so what I did here is if I go look at a hierarchy diagram, I have my generic valve filled closed failure mode, and it's the generalization of two particular ones that are applicable to each valve. I may want to do this if there are, if each of these valves are different, if they're actually different like part numbers, if they're different specific components, it may make sense for me to model these separately because the nuances of the ways in which they could fail closed may be slightly different. So this allows me to have a general concept and then a specific concept applied to each valve. So I did that for valve failed closed and valve failed open. If I go look at valve failed closed, I can then think about, okay, now I'm in the my frame of reference is going to be thinking out from a failure mode. So HV2, my valve failed closed. If I go back and look at my schematic here, if it's failed closed, there's a couple different ways what could cause it. Well, we could have potentially erosion or some material decay, right? That could cause the valve to fail closed. We could potentially send it an incorrect signal. So there's a couple different potential ways just doing some initial brainstorming that it could fail. And so what I could do is go in here, and I'm going to just sort of, for the purposes of talking through this, I'm just going to kind of do it from my targets and attributes for window over here. So I captured it as two different failure causes. It could be created by failure cause FC1, material decay of component, or FC3, improper command sent. Okay, and I have those. This is just my targets and attributes window over here, but I've modeled those obviously as failure causes that you can see over here. Okay, so I've given a description of what this actually means, and then the same thing for the improper command. Okay, so I've got a couple causes now captured, and then what would be the effects? Well, if that valve is closed, there's no ability for us to fill either the first or second stage tanks, right? So because there's that split in my diagram, if you see here, if this valve is apologize for that. My headset just turned off. Donna, could you just confirm you can still hear me?
Yeah, no, I can hear you, Brian. Sorry.
Okay, sorry about that. Okay, so if HV2 is closed, there's no possible way to fill either of the stages. So the effects, the localized effects would be inability to fill our first stage pneumatic tank, pressurization tank, and the second stage tank. So I've modeled those both as failure effects, and I've related them here with the effects relationship. Okay, all right, so I've got those, and then we got to think about, are there ways that we could detect this? Are there ways that we could figure out that this has happened? Well, one thing is if I've sent a command and I thought I opened that valve, I could detect it by a comparison of the upstream and downstream pressure. If I had pressure transducers upstream and downstream, and I think that valve's open, there should be a transient event in which the downstream pressure changes for a little bit. If the downstream pressure does not change at any point, then that would be an indicator. I also potentially would know if I had a limit switch on my valve. It could be either continuous, or there's different implementations. It could be continuous or it could be discrete, where it just contacted open or closed. But if I had a limit switch, I could also know if the valve is open or closed. Okay, so those are detection methods. And so I've modeled those both as failure detections. So I've got limit switches and I've got pressure comparisons. Okay, so I've got my three main things that I need to, if I think back through that process flow again, I've got my three main things now. I've got effects, I've got causes, effects, and detection methods. What I can do now is if I toggle each of these open on my targets and attributes, that's where I get to set the values for severity, occurrence, and difficulty of detection here. And so each of these, I'm going to think through about what the proper value should be. And if I click in here, I'll get scales for each of these. Okay, so once I set those, I have enough information to calculate my risk priority number, or RPN. All right, so that might be my first time through. So I might do something like that, my first analysis pass through. The first time I do an FMEA, I have an existing version of my system, and I'm going to evaluate it in its current state and come up with an RPN. And then from there, we will have to then work with the rest of our team to determine, based on those RPNs, which mitigation activities we're actually going to go conduct. And then once we do that, I can model those as mitigation activities and tie them back to whatever it's trying to mitigate. If it's the failure effect in this case, if I think each of these are going to be failure effects. So in this case, my first pass through, I'm trying to mitigate some of the effects of the failures. Okay, I'm going to flip back to slides and kind of talk about the rest of that process. So we kind of went through, we looked in the tool, we captured a little bit of that. What does it look like, you know, when you do that first pass through? We obviously went very quick. We only did it for a very simple system with a couple valves. But let's say we went through and we did the comprehensive analysis for our entire system of interest here at time equals 0. We did our failure modes and effects analysis. We calculated our risk priority numbers. And then, you know, we move on to the next phase of our project lifecycle. There might be a time at some point in the future we said, oh yeah, part of what we just talked about was we need pressure transducers upstream and downstream, right, of HV2. So I got to make sure that that's part of my physical architecture. I need to make sure I have those in my physical architecture. So as part of the next iteration, I'll start to update my physical architecture based on the results of the FMEA the first time. And I might do another FMEA analysis. And then that may lead to something else. I may have to make more changes if the RPN is still too high. And I may have to then do another FMEA analysis, and that may lead to more changes. So let's just, rather than jumping back to the tool, let's just talk through this in slides now. So at time t equals 1, our next time back, our second time through the analysis. Okay, so here's the table I generated using the Excel connector. And I've got my Helium HV2 and HV3 as my components. They both have 2 failure modes, open and closed. Each of them, we've identified a number of causes, a number of effects, detection methods. Right now, we have no way of preventing any of them. So I actually modeled that as a nil component, or not a component, a nil entity, a component, or an entity called none. So that something at least shows up here. Okay, so I've got a table, I've done my analysis. Let's go look at our failure detections. We've got our RPNs, but we see that there's some common themes here. We have a lot of what we're relying on as pressure comparison upstream and downstream. Because that's a transient comparison, if you don't have an operator looking at that quickly, and the hysteresis levels out at some point, even if the valve is open or closed, you may not even know. And so you have to be aware it's a transient event. So the difficulty detection is still fairly high on those. We may say that's not good enough, right? Well, my screenshot already shows you the solution. As I said, I'm going to implement a limit switch. But as part of the iterative analysis, I may go through and first look at these and say, yeah, those 5s and 6s are, I really actually want to know if there's a problem or not. I don't want to rely on chance of an operator looking at a screen at the right time. I need something better than that. So we may go back in and decide, okay, we've got our pressure transducers. Okay, that's our first step. We've got that. We've implemented that. We have a method. Sorry, I jumped ahead to my next one, but we have a method. Check the box. We at least have a way to detect the failure. Okay, now let's go back again and say that's too high. Sorry, I jumped ahead. We're going to say, all right, the 6s and the 5s are still too high on failure detection. We want to get that down. We want to have a better, you got to think about the difficulty of detection in terms of 1 means it's very easy to detect, 10 means it's very hard to detect. We want to get these scores lower. I want to add limit switches. The limit switches will then tell me, you know, exactly where the valve is in terms of open, closed, or some intermediate state. Okay, so that I'm now going to go in. We've agreed, we've talked as a team, we've agreed that we're going to implement limit switches, and I've implemented them here. You can see those now in my schematic. I've added limit switches. Okay, and I scored that so that now the probability that I detected is very high. I gave those a 2. It's pretty good that we're going to know if the valve is open or closed. Okay, so we went through, we've now done this FMEA approach a couple times. Now what do? We may may go back and say, okay, that's our third pass through now. Boy, this particular failure mode, HV2 failed open, has 4 different failure effects. It's going to affect a lot of things, and we may decide as a team. Some of them are quite serious. It could lead to a burst of a tube. It could create a catastrophic failure. And we may say, yeah, we don't want 9s on anything. The severity of 9 is unacceptable. Okay, we need to go address that. And because it has a number of effects, this is a candidate that we want to go mitigate. The last couple times, we went through and I just told you about adding the detections because they were obvious. Let's take a little bit different approach this time. Now let's say we got to think about this. There's a lot of these issues. We need to mitigate it somehow. So I'm going to add a mitigation activity. So I added this one about stepping down the pressure to a safe value. We don't want to damage downstream components. We don't want to burst components, potentially harm equipment or people. And so I created this new element, a mitigation activity, to investigate ways to do a pressure reduction. And it has to meet some criteria. It still has to have high enough pressure to be able to fill the bottles on the rocket to the proper pressure, but it has to be below the maximum expected operating rating pressure for the downstream component. So there's a sweet spot. So I'm capturing what I think there are the conditions, and the team will go off and figure out if that's something they can do or not. In this case, they went off and said, yeah, okay, we could put right here downstream of HV2, we could put a pressure regulating valve. The pressure in this tank is so much higher than what we need on the rocket. We can step it down. This pressure regulating valve will ensure that there's a safe pressure downstream of it. So, okay, yep, we're going to add in a new component that mitigates these effects. And then what we would do is we'd go in here and we would reevaluate the severity. Now, based on these effects are still possible, but the severity is going to be different, right? The severity is not going to be as bad, and we get a new RPN. So we would go through and continuously iterate this process till we get to the point where we feel comfortable with the RPNs. Okay, that's sort of the overall process and how we would use GENESYS to do that iterative approach. Let's talk about a couple of those visualizations. So, and I'll show you these in the tool. We have a hierarchy diagram, a hierarchy, regardless of the types of elements in your model, you can always use a hierarchy diagram. You can always use a spider diagram. What we've created are hierarchy definitions so that you have 2 that are already out of the box. One gives you all the types of components, elements that are related to our analysis and their relationships. And so you can see how those flow through in a hierarchical process. The other is a spider diagram view. These you're going to have to probably lay out the elements slightly, but I've kind of come up with this layout that I like. Up at the top, I've started to put my entity that introduces the failure mode up towards the top. The failure causes, above the failure mode, the effects down below, and then detection methods and prevention controls to the left and the right. Let me go show you this in the model because it's just so you can see how this looks, especially now that with GENESYS 2020 R2, you have the ability to apply rule sets. So as I said, I have a rule set now for color coding, and it does 2 things. One is if I apply it, all the typical types of elements that are related to failure modes and effects analysis get colored a different color. And I also created another one, a node rule, which, as I said, if I have, so that I don't have something that just doesn't show up on my diagram, if I so choose to create essentially a nil element, so if I don't have a failure prevention or I don't have a failure detection, I may just model it as none, an element called none. And if I do that, I'll at least, I'll call that out. I'll say if the name of any of those elements is none, show it with a red border so it visually pops out. Okay, so if I go look at one of these diagrams, and I'm going to go look at it in the spider. With R2, now let me go in and I'm going to clear the formatting here for a second. But once I first sort of lay out on my elements, as I said, I'll have it looking like this. And I've done a couple things. One is I applied a node template that gives me name, number, name, and class. So I also now see in the bottom compartment what the class is of the element, which is nice to see. If I apply my rule set now, I see a couple things. All the way that I set this up is that all of the types, the classes that are integral to failure modes and effects analysis get a solid border on the outside. And then the particular class gets a different color so that you can visually see, things that are detections are different than prevention controls, et cetera, et cetera. Once we tie something back into our architectural model, those are shown with the dotted outlined nodes here. So something that is either introducing a failure mode or any of these detections, causes, effects, prevention controls that are embodied in something else are also shown as dotted outlines so that you can visually distinguish that's a separate sort of category of relationships. And as I said, I also applied that additional rule. I modeled failure prevention control as an element called none, just so it shows up here. But that rule now outlines it in red so that it distinguishes it, and I actually realize that there's not really something there. So another nice thing about doing this in an object-oriented, model-based way is that it's not a standalone analysis. And by that, I mean, I can it's integral to the rest of my model development. It's integral to my design journey. So in the context of everything we were just talking about, I can see that I have identified for this failure mode 2 types of detections, right? The first was that pressure comparison downstream and upstream of that valve HV2. I can see that, yes, I've modeled that. I've essentially closed this out. It's embodied in a pressure transducer component upstream and a pressure transducer component downstream. That allows me to sort of check the box and say, yep, I've finished this portion of my analysis. It's now integrated back into the rest of my architectural model. Here, I get a visual cue that I'm not done. We agreed that we were going to add limit switches. I either haven't modeled the limit switches or I haven't created the relationship from the actual limit switch component back to the failure detection. So this tells me, oh, yeah, I actually have another step to do. So it's a nice way to sort of make sure that it's actually visual. You can create rules, right? You can create filters that will let you know if your analysis is A, complete, and B, properly tied back into that architectural model. So I think that's one of the key advantages of doing it in a model-based approach. So the last thing I'll show you here is the standard table definition that we've created. So this, I've applied a little bit of Excel just outlining so you can see things a little bit clearer here. But I recall I talked about specific versus general. You can combine the 2 concepts as well. You just have to, this is part of like your systems engineering management plan or your project execution plan, deciding what your implementation approach is. But I just wanted to show that you can combine the 2 concepts where it makes sense. So in my example here, I have failure modes that are specific, right? Because we've gotten to the point where we know what our actual valves are. They're actually different part numbers. They could fail closed and open in slightly different ways. So I made these specific, right? So these are specializations of their generic failure mode. The failure causes, I'm using as sort of general. And so these, as you can see by the names, are improper command sent. I'm not saying at this point what the specific commands are, or material decay of component. I'm not saying every particular specific component in the valve and the KO mechanisms for it. I'm leaving these as sort of generic concepts at this point. I'm doing the same thing for the effects. The detection is specific because in this case, I'm talking about specific pressure transducers, specific limit switches that are doing the detection. And the prevention typically also would be specific if we had that as well. So this just shows that you can combine the concepts. You just need to be explicit about how you're doing it, and that's part of your methodology that you define. So with that, we'll wrap up. So this new enhanced FMEA schema extension allows modelers to execute an FMEA in this integrated context within your architectural model. And I hope I've demonstrated that it's not a standalone disparate analysis. It's integral to the overall model. It helps you, one, actually refine the model and come up with a better design. It allows you to capture that design journey across, throughout that process. Traceability from those elements generating the failure modes through the mitigations back out to the elements in your architectural model that are impacted or changed by the FMEA. And as I showed, you can model it to the level of detail right for your project, right? If you want to just do the general, that's fine. If you need to do the specific, it's set up to do that as well. And I think one of the really neat things, in addition to the other key benefit for an organization or enterprise, is in addition to really integrating your analysis with your architectural model, is the second advantage of being able to create libraries. By that I mean, especially for those general cases, the general failure modes and causes, etc. One can then create a library of those that are reusable for other programs or projects within your organization. Particularly if you're building, variants of the same type of system. The types of failure modes, the categories of the causes, the categories of the effects probably will be similar, and that allows one to capture that, capture that knowledge, that enterprise knowledge, and apply it again to a future program. So with that, I'll stop, and we have a few minutes for some questions.
Thanks, Brian. We do have a few questions, thanks to all our participants. I encourage you to join the discussion now and then submit your questions using the webinar control panel. So our first question is, how detailed does an FMEA need to be to provide value?
Yeah, so I think that it changes based on the portion of the project life cycle that you're in. So early on, as I mentioned, you can either do the top-down or the bottom-up types of FMEAs. Early on, if you're doing a functional FMEA, it's going to be quite high level, and it's going to be a little bit of an abstract thinking exercise where one will have to think about how each function could go wrong. The implementation of each function could go wrong. So it will be a little bit more abstract, but it helps inform. It really helps inform the allocation of the functions to the physical architecture. So that one won't be that detailed, but it helps at the earlier phases of sort of figuring out really what the boxes, the constraints are in which you can develop your physical architecture. Later on, you'll start to switch to the bottoms up, the physical FMEA. And as you go through each of those design loops, I think typically what will happen is you'll go down another level of detail because you'll start to continue to refine your design. And so at like the benefit is the benefit is really it's really sort of at the same level as the level of fidelity that you are in your design process. So at a PDR level, it's going to be better than the conceptual level, and again at the CDR level. So you'll continue to refine, you'll continue to go down in levels of detail as you get closer and closer to actually synthesizing your product.
Okay, we have a question from Mustafa. Does the enhanced FMEA schema, the Lotus diagram you were showing, override the class's risk and concern in the meta model?
That's a good question, Mustafa. No, it does not overlap. It doesn't override them at all. They still have value and use, and they're used in slightly different ways. So concern is anything that is the probability of occurrence is 100%, essentially, right? It's a known issue, and it's something that you're capturing in your model that you're going to have to go address. A risk is something, the probability of some negative event that could occur in the future, so less than 100% probability. But it's typically tied back to potentially not meeting a requirement or not meet or having a programmatic risk, a programmatic issue, right? Something tied to cost or schedule, those sorts of things. And so it's really in what I'm calling specification space. It's the the conditions around which you're developing your project. The FMEA is more in the realization space. As you get into the behavioral and the physical architecture, that's when you start applying FMEA. So they all are, so it doesn't override those other concepts that you talked about. They're complementary to one another.
Okay. Our next question is, what's the difference between a failure detection and a failure prevention control? Can't they be the same thing?
I think in theory potentially, but a failure detection and a prevention control typically are different things. They potentially could be the same, but that's probably a corner case. A prevention control would be something that actually precludes the ability of the failure mode to actually occur. So in the extreme case, it would be designing it out. That would be a prevention control. There's simply no way that the valve could fail open because maybe you don't need a valve in some place, right? So maybe just take out the valve. In other cases, it may be prevented by state-based behavior, for example. One may preclude certain types of commands, improper commands, from being sent in certain states. And so that would be a prevention control. The detection is typically something different, right? It's the actual stimulus that allows you to become aware if it's happening. And my example was all about telemetry, typically, right? It was a limit switch, it was a pressure transducer. It's that stimulus that lets you know if it's occurring versus the stopping it from happening. You potentially could have a device that did both, but I think that would be a corner case.
Okay. The next question is, what's the difference between FMEA and FMECA? And do you do anything different if you're conducting an FMECA?
Yeah, so they're very similar. The FMECA, the FMECA, with the C stands for criticality. That's done a lot of times in US DoD and NASA applications. And the only additional thing you would do is you would add an additional score for criticality. In the NASA sense, it's a score 1 through 4. And it's a way of essentially just creating a list of, allows you to create something called a critical items list, a SIL. It's a way to just rank essentially the most critical from a safety perspective failure modes that could get you into trouble. And so, like I said, for NASA, it's typically one additional score that you would apply to each failure mode. It ranges between 1 and 4, 1 being the most severe, which means that there's potential catastrophic harm. There's the potential for catastrophic harm to humans or equipment. And in those cases, if you label something as a 1, you simply you're putting those in a separate table, or you're tabulating them in a separate way on this thing called a critical items list, and you report that out. Those are the ones that your customer essentially is saying those are the ones that you have to pay the most. You have to have the most awareness for.
Okay. One final question is from Robin, and when is GENESYS 2020 R2 estimated to be released? Robin, it's been released. It became available November 1st, so you can get that. The next part of her question is, and when is the expected release of the enhanced risk and opportunity capabilities? Brian, do you want to take that one?
Sure, and jump in as well. So there's just a couple last things we're doing. We're cleaning up the schema. We're doing some double checking just to make sure the schema extension is all correct. And Donna will go through and do some QA on it, but it's very close. Donna, I don't know if you have anything to add there, but I don't think it's going to be, it's not months, it's days probably, or a week.
Yes, if you want to get in contact with us, I imagine that at least the this part, the FMEA extension, can be made available shortly, to be used with 2020 R2. The opportunity, I'm not sure where that stands, if that's a separate part of the, a separate one.
Yeah, I think we're going to release that one as a separate extension as well. And, that should be done, quite quickly as well. I don't know if we say weeks or a month, but that one should be available pretty soon as well.
Okay. Thank you all. That wraps up the final Q&A. If you have any other questions or comments for Brian, please don't hesitate to send him an email. You can see his address on the screen. He would be happy to hear from you with any inquiries you may have. Thank you for joining us. Please join us next month, December 3rd at 11 Eastern, when David Long will host the webinar, Schema and Metamodels and Ontologies. Oh my. The link to register is on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. That's all for today. Once again, thank you for joining us and have a wonderful day.